In the last section, we started off on OSI Layer 3, and you learned about IP addresses and how we can combine those with the subnet mask to define the boundaries between our logical networks. In this section, we're still going to be on layer 3, but we're going to go much deeper into how we can control the boundaries between our networks with the use of subnetting. Now, if you've heard about this already, you've maybe heard it's one of the more complicated sections to learn for CCNA, but don't worry, we're going to go through it step by step. I'm going to show you loads of examples. I'm going to get you to work through examples as well, and by the time we're done, you're going to have this down. This is a short lecture where you're going to learn about CIDR, which is classless inter-domain routing. A problem with the original implementation of the classful addresses was that when the internet authorities gave out addresses, they always gave out a complete class A with a /8, or a complete class B with a /16, or a complete class C with a /24 subnet mask. And this gave the problem that if a company had more than 254 hosts, they were too big for a class C, they would have to be given a class B. And if they had, say, 500 hosts, they would actually get allocated addresses for 65,534 hosts. So that's obviously way too much, and this led to huge amounts of the global address space being wasted. So CIDR, classless interdomain routing, was introduced in 1993 as the solution, or a partial solution, for that problem. So CIDR removed the fixed /8, /16, and /24 requirements for the different address classes and allowed them to be split into smaller networks. And the name for this is subnetting. Again, we're going to be talking about subnetting a lot in the later lectures as well. So, for example, the Internet authorities could allocate the address 175.10.10.0/20. You can see from the first octet, 175, that that is a class B address, which would normally be a 16, but rather than allocating the organization the entire 16, the Internet authorities could now assign them a /20, which meant that other networks in that 175 range would be available to give to other companies. So rather than giving out the huge range, we split the classes into smaller networks that could be given to different organizations, and meant that there would be less addresses getting wasted. So companies can now be allocated an address range that matches what they actually need and doesn't waste extra addresses. We get another benefit from CIDR as well, which is route summarization. You see in the example here, we've got ISP-A, and they have allocated the address blocks that you see on the left. So one company got 175.10.0.0/24, another one got 175.10.1/24, 175.10.2/24, etc., all the way up to 175.10.255.0/24. So they've given out 255 address blocks there. We've also got ISP-B, and they've given out 175.11.0, 175.11.1, and so on, again /24s, all the way up to 175.11.255. And ISP-A and ISP-B get connected. Now, if we didn't have CIDR and we weren't able to do route summarization, ISP-A would advertise, it's actually 256 address blocks there, they would advertise all 256 address blocks to ISP-B, and ISP-B would vice versa advertise all their 256 address blocks to ISP-A. But when we've got CIDR and route summarization, what we can do is the two ISPs can advertise just an aggregate block. So ISP-A rather than advertising all 256/24s, it advertises 175.10.0.0/16, which is a superset of all those 256 smaller networks. So now ISP B, it only learns one route to all the networks behind ISP A rather than learning 256. And ISP B will vice versa just advertise one route of 175.11/16 to ISP A. So the benefits we get from this is that ISP A doesn't know about all 256 networks behind B. It only gets a single summary route that covers all of them. Obviously, if it's got one route rather than 256 routes, that's a lot less information. It's more efficient. It takes up less memory in the router. And if an individual link goes down in ISP B, it doesn't have any impact on ISP A because that one summary route doesn't change. It's going to be different in ISP B. Whenever one of their routes goes down, the other routers are going to have to recalculate that. But the benefit we get from this is we're compartmentalizing the different parts of our network. And if we've got an issue in part A of the network, it's not going to impact part B of the network. So it makes things a lot more stable and reliable, makes things more logical, which is better for us humans as well, because it makes it easier to troubleshoot them. Okay, that was CIDR, which is closely related to VLSM, our variable length subnet masks. We'll be getting to that real soon too. See you in the next lecture. At the end of this lecture, you're going to understand how we can implement subnetting. Now, I'm actually going to cover subnetting over a few lectures in this section. Subnetting is a really important topic, not just for passing the CCNA exam, but for networking in general. It's really one of the core knowledge areas that you need to understand if you're going to work in networking. So if you need it, take a quick break before you watch this lecture, then get yourself a cup of coffee and come back, and we're going to dive deep into networking. Okay, to understand this lecture, you need to think about it from the context of the originally intended IPv4 design, just like we did in the previous few lectures there, where all hosts which can communicate on the internet have a public IP address. Now, if you're already working in a company where you've already got exposure to working on the network, the chances are that your company is going to be using private IP addresses. Now, as we go through these lectures, do not think about it from that point of view. Okay, we're going to get into private IP addresses later, and I'll also explain how modern day networks work. But before we get there, you need to understand how IPv4 worked in the first place. It's a natural progression. Understand this first, and then you'll be able to understand why we use private addresses on our networks and how they work as well. Okay, so just bear with me and think about it from the point of view of how the internet worked like 10 or 15 years ago, before we were running out of addresses and before everybody was using private addresses. Oh, while I say that, by the way, the majority of companies are using private addresses, but there are a few out there that are using public addresses everywhere. That is pretty rare though. Okay, so for our example, let's say that we're a network designer for a small business with 4 departments that are spread over 2 offices, and we want to manage our own public address space. So what we could do is we could buy 4 separate Class C networks for that. But the problem is that public IP addresses cost money. So rather than doing that, rather than buying separate networks from the Internet Authorities, we could purchase a single range and subnet it into smaller portions. Like, let's say we've only got a handful of hosts in each of those departments. Rather than buying 256 addresses for each, we can buy a single Class C range, and then we can divide that network up into smaller networks and assign it to the different parts of our networks. So in the example, let's say we've got that class C range and it is 200.15.10.0/24, the default class C subnet masks. So to do our subnetting, to divide that network into smaller subnets, we need to borrow some host bits and add them to the network portion of the address. So we're going to move the line that separates the network portion of the address and the host portion further over to the right. So we're going to take some of our host addresses away and give them to the network portion of the address. When we do subnetting, the line always moves to the right. And the further to the right we go, the more subnets that we're going to have, but the less the amount of hosts that we'll have on each subnet. To calculate the number of available subnets that we're going to get by moving the line to the right, we use a formula of 2 to the power of subnet bits. Now, the first time I saw this, I thought, oh, I don't know how to do to the power of, never really covered that in school much. Don't worry, it's super simple, as you'll see as we go through these next few lectures. So if a class C network uses a /28 subnet mask, then we've borrowed 4 bits from the default of 24. Okay, normal class C mask is a /24. If we change that to a /28, the difference between 24 and 28 is 4. The way we calculate how many subnets we're going to get by doing that is it's 2 times 2 to the power of the amount of subnet bits that we borrowed. So we borrowed 4 bits for the network portion from the host portion. To see how many networks we're going to get, it's 2 to the power of 4. To calculate this, it's dead easy. You can do it on your fingers. You start off with 2 and you just double. So I go 2, 4, 8, 16. I'm going to now have 16 available subnets. Another example, if a class B network uses the same /28 subnet mask, well, the default for a class B is /16. So if we subnet that to a /28, we've borrowed 12 bits. To see how many subnets we're going to get, it is going to be 2 to the power of 12. So let's do this one. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096 subnets. For that one, you might have noticed it's easy if you remember that 2 to the power of 10 is 1024. Here we just keep doubling each time. And remember that hosts on different subnets need to go via a router if they want to communicate with each other. That's the whole point of having our IP addressing and of doing subnetting. It's to divide our network up into different logical parts of the network, and it's the routers that are the device that know how to get everywhere and that can direct the traffic. Okay, so that was how to calculate the number of subnets we're going to get. It's 2 to the power of how many bits that we borrowed. To calculate the number of hosts, it's 2 to the power of how many host bits there are minus 2. We need to subtract 2 because we've got the network address and the broadcast address that cannot be assigned to hosts. That's the 2 that we take away. So if a class C network uses a /28 subnet mask, then we've got 4 bits left for hosts. There's 32 bits in the address. If we're using 28 for the network portion, that leaves 4 for the host portion. 2 to the power of 4 is 2, 4, 8, 16, minus 2 for the network address and the broadcast address. That means that we would have 14 available addresses for our hosts. If we've got a class B network and it's using a /28, again, we've got 4 bits left for our hosts. So 2, 4, 8, 16 minus 2 is 14. It's exactly the same. So notice that the amount of hosts we're going to get is going to be dependent on the subnet size, and it's going to be the subnet mask size. It's going to be the same whether it's class A, class B, or class C. But the amount of subnets we'll get, if I go back a slide, it's going to be different for class A, B, or C because they've got different default subnet mask sizes. For example, if we use a /28 with a class B, then we're going to have 4096 available subnets. If we use a /28 with a class C, we're going to have 16 available subnets. There's a difference there. But for the hosts, it's always going to be the same. Okay, a quick note on IP subnet 0 command. Just like we have to subtract 2 to get the number of valid hosts, back in the day, we used to also have to subtract 2 from the number of available networks. This is because in the original internet standards, it wasn't allowed to use network bits of all zeros or all ones, just like we can't use host bits of all zeros or all ones. So that took away 2 of our available subnets. However, there wasn't really any practical need for that, and it wasted address space. There is a practical need with the host bits because we've got that network address and the broadcast address that are actually used, but as far as the number of subnets go, we were taking away 2, not really for any good reason. So on Cisco routers now, for quite a long time, there's a default command of IP subnet 0, which disables that behavior. The command is enabled by default, so those 2 extra network addresses are available in Cisco networks. It's important that I tell you this because you might look up something on the internet, you might look up a subnet calculator there, and it will tell you that there are 14 networks available on a class C with a /28, for example, when I'm telling you that there's 16. Okay, with Cisco networks and for the CCNA exam, do not take 2 away from the number of available subnets. Okay, and I want to tell you that just so you don't get confused if you're looking up anything on the internet. Okay, moving on, let's say that we've been allocated class C, 200.15.10.0/24, again the same as the last example, and here we're going to move the line all the way to the right. We're going to go with a /31. Obviously we can't do a /32 if we want to have more than one available host now. You can use a /32 subnet mask, but there's only one host there. That's mostly used for loopback addresses. Don't worry about it yet. We're going to talk about that later on. So if you do need to have multiple hosts, then the furthest right you can go is a /31. If we wrote that subnet mask in dotted decimal notation, it would be 255.255.255.254. We get the 254 because it's 128 plus 64, 32, 16, 8, 4 plus 2 comes up to 254. So that leaves 1 bit for the host address, which has obviously got a possible value of a 1 or a 0. So a class C, a /31, it borrows 7 bits for the network address from the host address. That gives us 128 subnets, which is 2 to the power of 7. Again, let's count it up. 2, 4, 8, 16, 32, 64, 128. And that's going to accommodate 2 hosts each. So that's what we get with a /31. The valid host addresses would be 200.15.10.0 to .1, 200.15.10.2 to .3, then 200.15.10.4 to .5, etc., all the way up to 200.15.10.254 and 255. You can check this by, we're using 200.15.10, so the first 3 octets are never going to change. The last octet, you just start with all zeros, and then it would be 0000001, and then a 0 or a 1, and then 0000010, and then a 0 or a 1, and so on. Okay, but wait. If we're using a /31, there's only 2 possible values to assign to hosts. What about the network and broadcast address? Yeah, a /31 subnet breaks the standard rules of IP addressing, where we have to have the network address and the broadcast address at the top and the bottom of the range. /31 subnets are, however, supported on Cisco routers for point-to-point links. If you think about it, a point-to-point link, there's just one side and the other side. Well, any traffic that comes from here needs to go to the other side and vice versa. There's nowhere else for it to go, so there isn't really any point in having a network and a broadcast address. So that's why Cisco allowed that exception. You can have a /31 on a point-to-point link. Okay, next up, moving on, we're going to move the line back a space. We're going to create a /30 now. The subnet mask in dotted decimal, 255.255.255.252, that and /30, they both mean the same thing. That is going to leave 2 bits for the host address, because we got 2 bits for the host address. 2 to the power of 2 is 4, minus 2 for the network and the broadcast address. That gives us 2 possible hosts. It borrows 6 bits for the network address. If we count this up, 2, 4, 8, 16, 32, 64 is our 64 bits, which can accommodate 2 hosts each. The valid addresses are, on the first subnet, the network address is 200.15.10.0 and the broadcast address is 200.15.10.3. The valid addresses are .1 and .2. The next subnet is 200.15.10.5 to .6, and the network is .4, the broadcast is .7. The next subnet, the network would be .8, the valid addresses would be 9 and 10, and the broadcast would be .11, and so on. Okay, as you look at this, the way that you can calculate what the different valid subnets are going to be, notice where the line is, it's after the number 4. So the network address is going to go up in values of 4. The first network address is .0, the next network address is .4, the next network address is .8, .12, .16, and so on. And because we know the network addresses, we can work out what the broadcast address and the range of valid IP addresses are going to be. So here it's going up in values of 4. The first subnet is going to be a 0. So 0 is the network address. And because the next range starts at .4, the broadcast address must be .3. So if 0 is the network address and .3 is the broadcast address, the valid host addresses must be .1 and .2. The next subnet, it starts with 4. The next subnet after that is at .8, so the broadcast address must be .7. So network address of .4, broadcast address of .7, that leaves the addresses in between of .5 and .6 are available to be assigned to our hosts. Okay, let's look at a comparison between the /31 and the /30 now. Hopefully you noticed that they both supported 2 hosts per subnet. But a /31 supported 128 subnetworks, a /30 only supported 64. So you're maybe thinking, oh, well, we're always going to use /31 then. And a /31 is useful if you need to maximize the use of your address space. But a /30 is more commonly used, it's more standardized. For the CCNA exam, if you get a question where you've got the choice where you could use either a /31 or a /30, always use a /30. So if the question requires you to come up with a subnet that supports 2 hosts, use a /30 unless the question explicitly tells you to use a /31. Okay, so we covered a /30 and a /31. Next up is a /29. So we're going to move the line back a space again. A /29 in dotted decimal is 255.255.255.248. Again, we get the 248 because it's 128 plus 64 plus 32 plus 16 plus 8 up to where the line is. That leaves 3 bits for the host address. 2 to the power of 3 is 248. 8 minus 2 because of the network address and the broadcast address gives us 6 available host addresses. And Class C, the default subnet mask is 24. Here we're using a /29, so we're borrowing 5 bits for the network address. 2 to the power of 5 is 2, 4, 8, 16, 32. So we've got 32 available subnets here. The valid host addresses, notice that the line is after the 8. So the network addresses are going to go up in values of 8. The first one will be 0, then 8, then 16, and so on. So the first subnet, the network address is 0. The next subnet, the network address is 8. So the broadcast address for that first subnet must be 1 less. It's going to be 200.15.10.7 for our example. So if the network address is .0 and the broadcast address is .7, that leaves .1 to 6 available to be assigned for our hosts. The next subnet is going to be, we said already, starts off with .8. The next one is at .16, so our broadcast address now must be .15, one less, which leaves the available host addresses of .9 to .14. And we can go on like this all the way up to 200.15.10.248 as the network address, .255 the broadcast address, with host addresses 249 to 254. And we can carry on moving the line back a place. So we did /31, /30, /29. We could also do a /28, which is 255.255.255.240. That is going to give us 16 networks of 14 hosts each on a Class C. Again, the default is a /24. If we're using a /28, we've borrowed 4 bits. 4 bits is 2, 4, 8, 16 available subnets. And after 28, it goes up to 32. So we've got 4 bits available for our host addressing. That is 2, 4, 8, 16 minus 2 for the hosts, which gives us 14 available hosts. We can move the line back again to a /27. That's going to be borrowing 3 bits, so that is 248 available networks, leaving 5 bits available for our hosts, which will be 2, 4, 8, 16, 32 minus 2 gives us 30 available hosts. You can see how I'm getting that now. A /26 is 4 networks and 62 hosts. A /25 is 2 networks and 126 hosts. And /24 is the default 1 network with 254 hosts. Okay, so that's how we carry out subnetting and figure out how many networks and how many hosts we're going to have. Next thing to tell you about is variable length subnet masks. With early routing protocols like RIP version 1, they only supported fixed length subnet masks, which meant you could subnet, but all subnets in a particular network had to be the same size. So all of your different subnets had to accommodate 14 hosts, for example, or 30 hosts, for example. And if you had one subnet that needed up to 30 hosts, you had to have all your subnets at a size of 30 hosts, even if one of them only had 3 hosts in it. Then, with later routing protocols, they came out with support for variable length subnet masks. That means that within the same range, you can have different sizes of subnets in there. So say I've got one part of my network which has got 10 hosts in it. I could give them 14 available hosts, and another part of a network that's got 28 hosts there, I could give them a subnet mask that gives them 30 available hosts. Okay, so variable length subnet masking, it means we can use different length subnet masks within the same network. This is a good thing because it lets us be much more precise with the size of our networks, and we're going to be wasting a lot less addresses. We'll cover how to do VLSM, variable length subnet masking, in the next lecture. Hopefully you've got a good handle on all of the subnetting information that we've covered so far, and you'd be able to work your way through a subnetting problem. But let's actually verify that now by doing a practice question. So the question is, what are the network address, the broadcast address, and the valid host addresses for the IP address of 198.22.45.173/26? And the second part of the question, what is the subnet mask in dotted decimal notation? So stop the video now, please, and figure that out. When you come back, I'll walk you through how we arrive at the answer. Okay, so let's look at how we are going to figure out the answer to the question. We're actually going to do the second part of the question first because it's more logical and easier to do it that way. So the second part of the question was, what is the subnet mask /26 in dotted decimal? And the way to do this, whenever you're working out a subnetting problem, particularly at the start, is to write out the bit pattern at the top of a piece of paper. Now later on you'll be able to do a lot of these in your head, but when you're first learning, it's way easier to write it all out like this. So take a piece of paper, start off and at the top, start off at the right and write 1, 2, 4, 8, 16, 32, 64, 128. And then you can put a dot in, and then 1, 2, 4, 8, and so on, until you've drawn out the bit pattern for the 4 octets in your subnet mask. Then the question that we had was we had to work out the dotted decimal notation for a /26. So just under your bit pattern at the top of the paper, write out 26 ones underneath that, and then you can put in 6 O's for the host portion of the address. Also draw a line in where the line is for the subnet mask, and then we can just add these up. So obviously the first octet is all ones, it's going to be 255. The second octet is also going to be 255. The third octet is also 255. And then at the fourth octet, where we're doing the subnetting here, the ones are in the 128 and the 64. So we add 128 and 64 together to give us 192. So a /26 in dotted decimal notation is 255.255.255.192. Okay, let's look at what the second part of the question was. What is the network address, the broadcast address, and a valid host address for the IP address 198.22.45.173/26? So again, we use our piece of paper, and we're going to write out the IP address now as well. You can see that I've done it on the top part here. That is the bit pattern for 198.22.45.173. That's how we would write it in decimal. And the network portion of the address is the first 26 bits. So I can see that that is 198.22.45, and then I just count whatever is in the first 2 bits here, and I've got a 1 for the 128 and a 0 for the 64, so that means it's 128. So the network address is 198.22.45.128. Don't worry about the text yet, by the way. This is a second way that we can figure out the answer that I'll get to in a second. I'm going to explain how to do it the long way first. So the long way is the logical way to do it at first. Again, we write out the IP address and the subnet mask in binary notation, and we put in the line where the subnet mask is. From that, we can figure out what the network address is. Like I just said, 198.22.45.128, I can see it here. Then we figure out what the broadcast address is. So that would be if we had a 1 in all of the host bits. So that would be a 1 on the 32 up to the 1. And if we add up 32 plus 16 plus 8 plus 4 plus 2 plus 1. Okay, that's 32 plus 16 is 48. Plus 8 is 56, plus 4 is 60, plus 2, 62, plus 1 is 63. So the network portion of the address was .128. 128 plus 63 is going to be 191. So again, the network address is 192.22.45.128. The broadcast address is 198.22.45.191. So we've got the network address and the broadcast address. The possible host addresses are going to be the addresses that lie between those two numbers. So that would be 198.22.45.129 going up to 198.22.45.190. Okay, so that's how we can figure it out very manually and very logically. We can take a little bit of a shortcut, and what we do is, again, you saw this in the last lecture, we look at where the line is. So the line is here after the 64, so I know that my subnets go up in multiples of 64. So the first one is going to be 198.22.45.0, then 45.64, then .128, and so on. I can see that this address that I'm interested in is 198.22.45.173. So first subnet is 0, then 64, then 128. The next one would be 128 plus 64, which is going to be 192. So this is less, 173 is less than the 192, so it must be in the 128 network. Okay, so I know this is in the network 198.22.45.128. I then add on 64. I know to add on 64 because that's where the line is, and the next network address would be 192. So if the next network address is 192, it must mean that the broadcast address for this subnet is one less than that. It's going to be 191. So there, I've figured out my network address is 128. I figured out that my broadcast address is 191. The available hosts must be everything in between. That would be 198.22.45.129 to 198.22.45.190. Okay, so that is how we can figure it out. And a final important point to tell you here is notice that everything was done on where the subnet line is. And this example is /26, so that is in the last octet. So we don't actually need to worry about the first 3 octets. They're always going to be unchanged as 198.22.45 in our example. So you can save some time by only writing out the octet that the subnetting is happening on. You don't have to write the whole thing out in full every time. Okay, so that was a quick example of how we will solve a subnetting question, the kind of thing that you could see on the CCNA exam. In this lecture, we're going to carry on with our subnetting theme, and by the end of the lecture, you will be able to carry out a variable length subnet mask design for a real-world network topology. Now, it's only a small network in the example that we're going to work through, but you can apply the same things that you're going to learn here to larger networks in the real world. The slide that you see here is the same slide that you saw at the end of the last lecture, where we explained that back in the day with early routing protocols, whenever you did subnetting, each of the subnets had to be exactly the same size. So if you had one subnet that was a /28, for example, they all had to be a /28. You couldn't mix and match /27, /28, /29 within the same larger network. But that ended up wasting a lot of addresses, so with later routing protocols, they did have support for variable length subnet masks, and now we can mix and match the size of our subnets within that greater network. And we're going to work through an example here. The things that we need to consider when we're going to do the design are how many different locations do we have in the network that are going to need subnets, and how many hosts are going to be in each of those subnets. What are the IP addressing requirements for each of the different locations? So should different departments or types of hosts be in different subnets? For example, you might have one office, but within that office, maybe you've got a sales department, a research and development department, and an accounting department, and you want the accounting department to be secured from different departments. Well, in that case, you would definitely put it in its own separate subnet. Because different subnets, we have to route between them at a router, it's easy to secure them at the layer 3 level based on their IP address. And the last question here, what size is appropriate for each subnet? We don't want to waste addresses, but we want to leave some room for growth. So we need to have a bit of a balance here. Don't make it too big, we're wasting addresses, but don't make it too small that we're going to run out of addresses and then going to have to do a redesign later. That would just be giving ourselves a big headache. So for our example, this is our network topology diagram. We've got an organization, they've got an office in New York and a branch office in Boston. New York is their headquarters, and they've got 28 hosts in the engineering department and 14 hosts in sales. In Boston, they've also got engineering and sales. They've got 28 in engineering, the same as in New York, and they've only got 7 hosts in the sales department. So those are the different parts of the network that we need to apply IP addresses to, and we've been allocated the class C network of 200.15.10.0/24 from our internet service provider. Another thing that we need to do is don't forget about our point-to-point links between the routers. They need to have connectivity between each other, so they're going to need IP addresses too. It's a point-to-point link, so we've just got two host IP addresses there. The outside interface on the New York router is connected to the outside interface on the Boston router. So that was our requirements. So now we need to think about how are we actually going to design this. And the steps that you work through. First off, find the largest segment and allocate a suitable subnet size for it. You then create that subnet at the start of your available address space. And then that's it. You just keep working your way down. So you start off with the largest subnet, you then move to the next one, the next one, and the next one until you've allocated addresses for all of your different subnets. Now, in a real-world deployment, you want to have a scalable design. So you want to have room for growth in your networking design. So let's say that I've got a subnet that has got 14 hosts on there. Well, you know that one of our subnet sizes is exactly for 14 hosts. Don't give the subnet that size, because maybe in a few weeks' time, a couple of extra people are going to join the department, and now how are you going to fix that problem? So make the subnet size big enough that it's going to be able to grow. Another thing is, because we're going to sequentially go from largest down to smallest, maybe we're going to have a subnet with 30 hosts there, and then another subnet with 30 hosts, and then a subnet with 14 hosts. Well, leave a spare subnet with 30 hosts in it. So don't just do 2 subnets of 30, do 3 or 4 subnets of 30. Because then if you do have a new department that requires up to 30 hosts later, you've got a spare subnet there waiting for it, and everything is still sequential and contiguous, and logical, going from largest down to smallest. Okay, so hopefully you got the point there. Don't design for what is right now. Design for what is going to be the best fit in the future. Leave some scalability there, leave some room for growth. So that's what you do in the real world. Don't do that in the CCNA exam. Okay, do not think about, oh, this is what I would do in the real world, this would be best practice. Do exactly what the exam question tells you to do, even if you think that would be a stupid thing to do. Okay, don't overthink things. Don't think, oh, well, it would be better to do it this way. Do exactly black and white what the question asks you to do, and then you're going to get the question right. Okay, so for our example, we had the engineering departments in New York and Boston, and they have got 28 hosts each. And that was the largest subnets that we required. For our example, let's say the exam question says that the departments will not grow, and we need to use the smallest subnets possible to maximize our available address space. Okay, so do not leave any room for future growth here, because the question says make it optimal. Maximize the use of the address space. Okay, so that's the question. What I want you to now is pause the video here and calculate the optimal subnet mask for the engineering departments. So no bigger than is necessary, but make sure it's at least big enough to support 28 hosts. Once you've done that, you'll be able to determine the network and broadcast addresses. Do that for both engineering departments, both New York and Boston, and figure out what the range of host addresses will be. Okay, so go on ahead and do that. Please pause the video now. When you come back in a second, I'll walk you through how to get the answer. Okay, so let's look at how to get the answer. So we'd been allocated 200.15.10.0/24. We've been allocated a class C. And we've got 2 different departments that we want 2 different subnets for, and they had got 28 hosts each. A /27 supports 30 hosts. A /28 is 14, so it's not big enough. We can't use that. The smallest that we can use, which is what we were asked to do, is a /27. Real world, you might argue that you'd prefer to use a /26. This is not the real world, it's an exam question. We're going to use the smallest possible, which was a /27. If we wrote that in dotted decimal notation, it's 255.255.255.224. Okay, so that was the first part of the question, figure out the subnet mask. The next thing we have to do is actually divide up our address space. The headquarters was in New York, so let's give them the first subnet. So the network address is going to be 200.15.10.0/27. And if we look at the line, we can see it's after 32. So a /27 is going to go up in increments of 32. So the next network address is going to be 200.15.10.32, which means that the first subnet's broadcast address is going to be one less than that. It's going to be 200.15.10.31. And that leaves addresses available for our hosts of 200.15.10.1 up to 30. Okay, so that's the engineering subnet. Next is the Boston engineering subnet. Well, the last broadcast address used was .31, so the network address we're going to be using is .32. So network address 200.15.10.32/27. Again, we're still using that /27, where the line is after the 32. So the next network address would be .64. So our broadcast address must be 200.15.10.63, which is one less, and our hosts are going to be what's between the network and broadcast address. That's 200.15.10.33 up to 62. Okay, so that was the engineering departments taken care of. All right, that's coming up to the 10-minute mark in this lecture. So if you want to take a break, now's a good time to go and stretch your legs. When I see you back here for part 2, we'll go through the subnetting for the rest of the departments.